A body that does not undergo a change in its shape and size on application of a force is called a rigid body. In a rigid body, there is no relative movement between the particles, whereas a non-rigid body undergoes a change in shape and size on application of a force. When a rigid body rotates about a fixed axis, all the particles of the rigid body undergo circular motion with different radii about a center fixed on the axis of rotation. The motion of fan, potter's wheel, and earth spinning about its axis and spinning top are examples of rotational motion. Let us concentrate on one particle of the rotating rigid body that moves in a circular path of radius r. In a time t, it undergoes a linear displacement s along the circumference, and the displacement per unit time is called its linear velocity, which points along the tangent to the circle. The angle subtended at the center in the same time t is theta, and the angular displacement per unit time is called the angular velocity. The direction of the angular velocity is along the axis of rotation. A force acting on a rigid body produces turning effect, which is measured in terms of torque. The turning effect of a force depends on the distance of the point of action of the force from the axis of rotation as well as on the angle at which the force is applied. Due to this reason, the doors are designed with handles close to the edge and not near the hinges, or else it will be difficult to open the door. Applying the force in a direction other than the perpendicular direction also makes it difficult to open the door. A particle undergoing rotational motion is also said to possess the angular momentum, which is defined as the product of its distance from the axis of rotation and the linear momentum. Its direction is along the axis of rotation and points along r cross p. In linear motion, when a force F is applied on a body of mass m, the body acquires an acceleration a is equal to F by m. For a given force, the acceleration only depends on the mass of the body. In rotational motion, however, the effect of the force not only depends on the mass of the body, but also on the distribution of mass about the axis of rotation. Here we apply the same force on the rod in two different situations, and the rod experiences unequal angular acceleration in the two cases. As the axis of rotation is different in the two cases, the mass is distributed at a larger distance in the first case and at a comparatively smaller distance in the second. The physical quantity that depends on the distribution of mass about the axis of rotation is called the moment of inertia. The moment of inertia of the rod in the two cases can be calculated and shown that it is greater in the first case. Moment of inertia of a system of 4 particles is given by I is equal to m1 r1 square plus m2 r2 square plus m3 r3 square plus m4 r4 square, where the distances r1, r2, r3 and r4 are the perpendicular distances of m1, m2, m3 and m4 from the axis of rotation. We can now draw a comparison between linear and rotational motion and list the rotational analogues of physical quantities used to describe linear motion. Also, the relations between various physical quantities in rotational motion take the same form as between their counterparts in the linear motion. A ballet dancer starts spinning with her arms overhead. When she spreads her arms, her rotation slows down, whereas when she pulls the arm closer to her body, her rotation becomes faster. This happens because when she stretches her arms, her mass is at a larger distance from the axis of rotation, which passes through her body. Thus, the moment of inertia increases. Since no external torque is acting, the angular momentum has to remain conserved. With increase in moment of inertia, the angular speed decreases. Similarly, when she pulls her arms close to her body, some of the mass comes near the axis of rotation, and therefore the moment of inertia decreases, and hence the angular velocity increases. Can you distinguish a boiled egg from a raw egg by spinning them? You can do so by observing what happens when a force is applied to spin them. A raw egg spins slower than a boiled egg when given the same amount of torque. It is because the liquid particles inside the raw egg gets pushed away from the center towards the shell, and hence the moment of inertia of the raw egg is more than that of boiled egg, and it acquires a lesser angular velocity. Moreover, when you try to stop them from spinning, the boiled egg comes to rest quickly, but the raw egg starts spinning again if you let it go. This is because in boiled egg, the entire mass comes to rest as soon as the force is applied, whereas in raw egg, only outer shell comes to rest. The liquid inside the shell keeps rotating, and hence egg starts spinning again. Have you ever anticipated the effect of global warming on the duration of the day? What would happen if all the polar ice melts and the water flows into the oceans? The duration of the day on the Earth will increase. Initially, when the ice is on the poles near the axis of rotation, the moment of inertia of the Earth is less. But when this ice melts and water flows and spreads on the Earth's surface, the moment of inertia of the Earth will increase. In the absence of the external torque, the angular momentum of the Earth will remain constant, and hence angular velocity will decrease. This results in longer duration of the day on the Earth.